far out past the last warm light of the inner planets, where the sun has shrunk to something not much brighter than the brightest star in an earthly sky, the solar system grows cold and wide and very still. The distances between things stretch until they become the dominant fact of the place. A grain of ice drifts, a molecule of water, frozen to the surface of a dust particle no wider than a wavelength of light, moves along a slow arc that will take centuries to complete. Out here, in the earliest chapters of the solar system's formation, before any planet had assembled itself from the diffuse cloud of gas and dust that surrounded the young sun, material like this, small, cold, and chemical, was the substance from which everything waiting in the outer dark would eventually be built. Billions of years have passed since that time. The grains have long since come together. The dust and ice and gas that drifted in those cold outer regions of the early solar nebula slowly gathered, grain by grain and particle by particle, into two worlds that now circle the sun at distances so great that the light reaching them left its source 4 hours ago. These are not the largest planets. They do not have the commanding presence of Jupiter or the lovely rings of Saturn. But Uranus and Neptune carry within them something neither of those larger worlds possesses in abundance, the chemical residue of the cold outer nebula from which they formed, pressed and heated now beyond recognition, but present still, making up most of what these planets are. What that means, in the language of mass and composition, is that Uranus and Neptune are built differently from their larger neighbors in ways that planetary scientists have spent decades working to understand. The difference begins with the simplest question one can ask of a planet: what is it made of? For Jupiter and Saturn, the answer is mostly hydrogen and helium. Those two elements, the lightest in the universe, make up roughly 90% of Jupiter's total mass. Saturn is similar in its broad chemistry, so light in its overall constitution, that its mean density, the average mass packed into each cubic centimeter of its volume, falls below that of water. Saturn, if placed in an ocean vast enough to hold it, would float. The entire planet, all its rings and all its storms, would rest on the surface of a sufficiently large sea, because so much of it is simply gas. Uranus and Neptune do not float. They are made of heavier stuff, denser stuff, stuff that carries the chemical signatures of compounds rather than pure elements. Water is there, deep inside, and ammonia and methane molecules built from hydrogen and oxygen, from hydrogen and nitrogen, from hydrogen and carbon, and these compounds constitute perhaps 80 to 85% of everything that makes up Uranus and Neptune by mass. Hydrogen and helium are present too, but only as a thin outer wrapping, a shell that accounts for somewhere between 15 and 20% of each planet's total weight. The rest, the vast majority, belongs to these denser molecular compounds and to the rock and metal that sit at their centers. This is the distinction that separates the two planet classes, and it is a distinction drawn not by the size of the planets, not by where they orbit, but by what their interiors are fundamentally composed of. Jupiter is a gas giant. Saturn is a gas giant. The hydrogen and helium that flood their interiors in enormous quantities set the terms for everything about those worlds: their low density, their deep and electrically conductive metallic hydrogen layers, the mechanisms by which they generate their magnetic fields. Uranus and Neptune, sitting farther out and built from different raw materials, have their own terms, their own internal logic, their own planetary character. They are ice giants, and the distinction is not a matter of naming alone. It reaches into the physics of their interiors and shapes everything that happens inside them. The word ice, as planetary scientists use it here, does not mean frozen. This is important, and it is one of those cases where a familiar word has taken on a technical meaning that bears almost no resemblance to its everyday sense. On a winter morning, ice is the hard, cold, transparent solid that forms on a puddle overnight, a substance that crunches underfoot and melts in a warm hand. The ice inside Uranus and Neptune is none of those things. In the vocabulary of planetary science, ice refers to a category of compounds made from hydrogen combined with oxygen, nitrogen and carbon, water, ammonia, and methane, that condensed out of the gas of the early solar nebula in the cold regions far from the young sun and became solid grains that eventually built the bulk of these planets. Those grains are long gone. The materials they carried are still there, but under conditions so extreme that the word solid has ceased to apply, and frozen has ceased to apply, and the word ice has come to mean only the chemical identity of the compounds, not any physical state they currently occupy. Deep inside Uranus and Neptune, water is not ice in any sense a winter morning would recognize. It is hot, it is under crushing pressure, it is broken into ions and moving. It retains only the signature of what it was in the cold outer nebula, the chemical recipe, while everything about its behavior has been transformed by depth and heat and weight. The outer solar nebula, in the time before these planets formed, was a place of extraordinary cold and chemical richness. Far from the sun, where the young star's warmth did not reach, temperatures fell low enough that volatile compounds, water vapor, ammonia gas, methane gas, could condense directly onto the surfaces of dust grains, coating them in thin films of ice. This is the frost line, or rather a series of frost lines at different distances from the sun, where different compounds passed from gas to solid as the temperature dropped below each compound's condensation point. Uranus and Neptune formed beyond these lines, in the zone where all three of these compounds existed as solid coatings on the small grains that slowly, over millions of years, collided and stuck together and built up the embryonic cores of what would become planets. The outer solar system was cold enough to let these materials accumulate. And accumulate they did until the cores grew massive enough to begin pulling in the surrounding hydrogen and helium gas, wrapping themselves in those lighter elements, and arriving at the compositions they have maintained ever since. Something about the rate at which this happened, or the amount of hydrogen and helium gas that remained available by the time these planets were large enough to accrete it, meant that Uranus and Neptune gathered far less of those lighter gases than Jupiter and Saturn did. Jupiter formed closer to the Sun, where conditions may have allowed its core to reach the critical mass needed to begin rapid gas accretion earlier, and the solar nebula was still thick with hydrogen and helium when Jupiter was growing quickly. By the time Uranus and Neptune had assembled their rocky and icy cores out in the farther cold, the window for large-scale gas accretion may have begun to close. What they captured was modest in comparison, enough to give them their outer envelopes of molecular hydrogen and helium, enough to shape their atmospheric chemistry, but not enough to bury the icy core under hundreds of Earth masses of gas, the way Jupiter did. The icy and rocky materials remained the dominant components by mass, and the two planets emerged as something categorically different from their inner giant neighbors. In terms of raw size, Uranus carries a mass roughly 14.5 times that of Earth. It is large by any ordinary measure. The entire Earth could fit inside Uranus's volume more than 60 times over, and yet in the context of the outer solar system, Uranus is the smaller of the two ice giants. Neptune is slightly more massive, carrying approximately 17 Earth masses, and it is also denser. Uranus has a mean density of about 1.25 grams per cubic centimeter, while Neptune's density runs closer to 1 2/3 grams per cubic centimeter. That difference in density between two planets that are otherwise so similar in composition hints at something about their internal structures that models have so far struggled to fully resolve. The same basic recipe of ices and rock and a light hydrogen envelope pressed to different configurations, producing planets that look like twins from a distance, but differ in measurable ways at the level of their bulk properties. A useful way to hold the compositional difference between gas giants and ice giants is to think in terms of a single kilogram of each planet's total mass. Inside Jupiter, if that kilogram were a representative sample of the whole planet, nearly 900 grams of it would be hydrogen and helium. The remaining 100 or so grams would belong to heavier elements and compounds, the rocky and icy materials concentrated toward Jupiter's deep interior. Inside Neptune, the proportions invert. Fewer than 200 grams of that kilogram would be hydrogen and helium. The remaining 800 grams would be water and ammonia and methane compounds, and the silicate rocks and metals that form the deepest core. 800 grams out of every kilogram in the planet is the denser molecular stuff that came from cold outer nebula material, and that difference in proportion is what makes Neptune an ice giant and Jupiter a gas giant, as plainly as any definition can draw the line. Saturn, floating near this comparison in the mind's arrangement of planets, sits firmly on the gas giant side of that line. Its mean density is the lowest of any planet in the solar system, lower than water, at about 69 hundredths of a gram per cubic centimeter, which is why the image of it floating in an ocean holds up arithmetically. Neptune, sitting far out in the cold dark with its denser icy interior, has a mean density more than twice that of Saturn. Despite being far smaller and less massive than Saturn, despite containing far less total material, Neptune packs what it has more tightly because the materials inside it are intrinsically heavier than the hydrogen and helium that constitute most of Saturn. The scale of a planet and the density of a planet are different measures, and in the outer solar system, they do not always move together in the direction one might expect. The chemical compounds that make up most of Uranus and Neptune, water, ammonia, methane, are not exotic substances. They are among the most common molecules in the universe. Water is made from the two most abundant reactive elements, hydrogen and oxygen. Ammonia is made from hydrogen and nitrogen. Methane is made from hydrogen and carbon. All four of those elements, hydrogen, oxygen, nitrogen, carbon, are among the most abundant in the cosmos, forged in stars and distributed widely across galaxies over billions of years. The prevalence of these compounds in the outer solar system is not an accident or a peculiarity. It is the predictable consequence of having the right elements in the right temperature range for condensation to occur. Beyond the frost lines, where it was cold enough, these molecules solidified and became the building blocks of the outer planets. Water ice, ammonia ice, methane ice, simple chemistry, abundant elements, cold temperatures, and from that combination came the two worlds that now orbit billions of miles from the sun, with these materials locked inside them under conditions of heat and pressure that would render them unrecognizable to any laboratory at ordinary scales. There is something worth sitting with in the fact that the interiors of these distant, cold-seeming planets are not cold at all. The surface temperatures of Uranus and Neptune, high in their outer atmospheres, are among the lowest in the solar system. Uranus in particular ranks among the coldest planetary atmospheres measured anywhere, with cloud-top temperatures approaching 200 degrees below zero on the Fahrenheit scale. But this outer cold is a misleading signal about what the planet contains. The interior of Uranus and the interior of Neptune are hot. Under the weight of all that overlying material, the pressures rise and the temperatures rise with them, and the ices that make up the bulk of each planet exist not as anything frozen, but as dense, hot fluids carrying electrical charge. The cold of the outer atmosphere is a skin, a surface condition shaped by distance from the sun and by the slow radiation of whatever heat these planets possess. It says very little about the physical state of the matter inside. The inside of an ice giant is warm and dense and chemically active in ways the outer atmosphere gives no hint of. The contrast between Jupiter's interior and the interiors of Uranus and Neptune sharpens further when one considers what Jupiter can do and these planets cannot. Within Jupiter, the pressure climbs so high, past what would be about 1.5 million times the pressure of Earth's atmosphere, that hydrogen is compressed into a metallic state. In metallic hydrogen, the electrons that normally belong to individual hydrogen atoms have been squeezed away from their nuclei and move freely through the material, the way electrons move through copper or iron. The result is a substance that conducts electricity, that flows and circulates, and whose motion within Jupiter's rotating interior generates the powerful and well-organized magnetic field that surrounds that planet. Uranus and Neptune never reach those pressures. They are too small, and the icy and rocky materials that make up most of their volume reach their own exotic states at lower pressures than hydrogen requires, leaving no room for an extended metallic hydrogen layer of the kind Jupiter sustains. Something else must be generating the magnetic fields of these two planets, something stranger and more specific to their actual compositions. That something lies in the deep interior, in the behavior of water and ammonia under the pressures and temperatures that do exist at these depths, but that is a matter for the interior itself, reached only after passing through the layers above. A single grain of ice drifting in the early solar nebula carried within it, in a sense, the chemical promise of what these planets would become. Not because that grain had a destination, not because the solar system had a plan, but because the chemistry of the outer nebula was what it was, and the physics of condensation and accretion would do what those laws always do when given enough time and enough material. The grains accumulated, the cores grew, the planets formed, and what had been cold and dispersed and drifting in the dark became, under the transformation of compression and time, the interiors of two worlds so filled with material, exotic beyond ordinary experience, that the vocabulary for describing them had to be invented or borrowed from places it barely fit. The chemical divide between the ice giants and the gas giants is, in the end, a record of where in the solar nebula each planet grew and what building materials were available there. Jupiter and Saturn grew in a zone where hydrogen and helium were the dominant materials available for accretion in large quantities, and they swept up enormous amounts of those gases. Uranus and Neptune grew farther out, where the icy compounds condensed in abundance, but where the available hydrogen and helium gas was either less plentiful or ran out before these planets could gather as much. The compositions they ended up with are, in this sense, a kind of fossil record of the early solar system, a preserved signal of the chemical geography of the disk that formed around the young sun 4.5 billion years ago. The ratio of ices to gas in their interiors is not a random fact. It is a measurement, carried quietly inside these planets, of conditions that no longer exist and cannot be directly observed. In the broader context of planetary science, Uranus and Neptune have a significance that reaches well beyond the solar system. The study of planets orbiting other stars has revealed something striking about the distribution of planet types across the galaxy. The most common category of planet found orbiting other stars by a considerable margin in many surveys appears to be a type intermediate between Earth and Neptune in size and composition, planets with masses and bulk densities suggesting they too are built largely from icy and rocky compounds rather than from hydrogen and helium gas. These planets have been called sub-Neptunes, a name that positions them in relation to Neptune as the local reference point for their class. They are common. They appear around a wide range of star types, in a wide range of orbital configurations, in systems scattered across the galaxy, in numbers that suggest this kind of planet may be among the default outcomes of the planet formation process, wherever the right conditions exist. This is what makes Uranus and Neptune more than just the outer two planets of a particular solar system. They are the only members of this dominant cosmic category, close enough to have been visited by spacecraft, close enough to have had their gravitational fields measured, close enough to have had their magnetic environments sampled, close enough to serve as ground truth for the composition models that try to explain what all those distant sub-Neptune planets contain. When scientists work out theories about the interiors of the most common planet type in the galaxy, they calibrate those theories against what is known and what remains unknown about Uranus and Neptune. The two ice giants are, in this sense, local examples of a universal abundance. They are not outliers, they are representatives. There is something quietly reorganizing about that shift in perspective. For a long time, in the history of how the solar system was understood, Uranus and Neptune were treated as remote and secondary, the far planets, hard to reach, dim in telescopes, largely featureless, visited once by a single spacecraft on its way out of the solar system. They were at the edge of what was known and the beginning of what was beyond knowing. That picture has not entirely changed. They remain distant and poorly measured compared to the inner planets, but the frame around them has shifted. The most common type of planet in the galaxy happens to look, in bulk composition and rough structure, like these two worlds that have been orbiting at the outer edge of human attention for generations. The sub-Neptunes circling distant stars by the billions are in a class with Uranus and Neptune. The familiar becomes the archetype, the distant becomes the template. Far out in the cold dark of the outer solar nebula, in the time before any planet existed, a grain of ice drifted along its slow arc, carrying a molecule of water or ammonia on its surface, waiting without intention, without awareness, by nothing more than physics, to become part of something larger. It became part of something larger. The ice giants that formed from materials like that grain are still out there, still circling, carrying within their depths the compressed and transformed residue of that original cold chemistry, and the same process that built them, operating around other stars in other systems across the galaxy, has built worlds like them in numbers too large to count. Ordinary worlds, in the fullest sense, common as any planetary class the universe has produced. Uranus and Neptune, at the edge of the familiar solar system, are far from alone in what they are. The slow drift continues, in a sense, in the orbital motion of those two planets around the Sun, a journey that takes Uranus 84 years to complete, and Neptune nearly 165. One Neptunian year has passed only once since the planet was first observed, and that year was not quite complete when the count reached its end. These are patient worlds. They move through space at their own unhurried pace, heavy with icy material, wrapped in their thin envelopes of hydrogen, carrying inside them the answers to questions about the most common planetary outcome in the galaxy. answers that have not yet been fully read, held in interiors no instrument has directly sampled, waiting with the same absence of urgency that the cold outer solar system has always had, the vast and ordinary stillness of worlds with nothing to prove, and all the time there is to simply continue being what they are. The compounds that make up most of these planets, water, ammonia, methane, are not rare. They are not the products of unusual chemistry or improbable conditions. They are, in the context of the universe, as ordinary as any material can be, the expected result of common elements combining under conditions that exist in cold, dark, hydrogen-rich clouds throughout the galaxy. That ordinariness is the point. The ice giants are not exceptional. They are exemplary. They stand as the local members of a category that the galaxy appears to produce wherever the right building materials and the right temperatures come together, which is to say, in a very large number of places, on numbers that dwarf the count of rocky planets and gas giants combined, in numbers that make the sub-Neptune the most common world type in a cosmos of 100 billion galaxies, each containing 100 billion stars. Among all of that ordinary abundance, Uranus and Neptune are the two that circle close enough to matter directly to the science of understanding what all the others are. And so what had seemed like the far edge, the cold margin, the lesser outer planets, these two blue-tinted worlds at the reach of the familiar solar system, turn out to be something else entirely. They are the nearest examples of the universe's most common planetary theme, carrying in their interiors the chemistry that the outer solar nebula produced in abundance, transformed now beyond easy recognition, but chemically still itself, still the record of what condensed in the cold, dark 4.5 billion years ago, when the solar system was young and the grain of ice drifted, and the grain of ice accumulated, and the planet slowly, patiently, without intent, became far out in the solar system, where the sun has contracted to a point of hard white light, no larger than a bright star on a clear night. Two planets hang in the dark against a background that has no edge. One is the color of pale seafoam, the other is the color of deep water seen through clean glass. From a distance, the difference between them is a matter of shade, the same family of blue, only one cooler and lighter, the other richer and saturated, and unmistakably itself. That difference in color, so quiet at this remove, comes from a single thin constituent of each planet's outer layer, a gas present in small amounts that has been sorting light by wavelength for billions of years without ceasing. Methane does this. In the outermost atmospheres of both worlds, methane molecules drift in concentrations of roughly 2 to 3 parts in every 100 by volume, a small fraction of the whole, but enough. When sunlight arrives, already weakened by its long passage from the sun, those molecules absorb the red end of the visible spectrum and leave the blue and green wavelengths to scatter back into space. The red light does not return. It is taken in, its energy dispersed into the molecular fabric of the atmosphere, and what remains to travel back toward any observer is a cool and dominant blue. On Uranus, the effect produces something pallid and even a color without great depth. On Neptune, it produces something that feels almost concentrated, a blue that has weight and presence. The same mechanism, the same gas, the same photochemistry, and yet the results are not quite the same for reasons that planetologists are still working to fully understand. Stand in imagination at the outer edge of Neptune's disk. The planet fills a wide arc. Its surface, if a planet with no solid surface can be said to have one, is cloud. Layers of frozen and condensed material arranged in bands and sheets, moving, not gently, Neptune hosts some of the strongest winds measured anywhere in the solar system, speeds that reach upward of 2,000 kilometers per hour near the largest storm systems, and a wind so fast it would cross a continent on Earth in minutes and would strip any ordinary structure from any ordinary surface without slowing. There is no surface here to strip. The wind moves across itself, atmosphere against atmosphere, the planet's rotation carrying the whole system around in a continuous circuit that has not paused in the time since the planet formed. The great dark spot that Voyager 2 photographed in 1989, a dark oval absence in Neptune's cloud layer, wide enough that Earth would fit inside its borders with room remaining, rotated within that wind field like a smooth stone caught in a current. The clouds around it moved. The spot itself moved, holding its shape while the surrounding atmosphere slid past. It was a storm, or it was a gap, a window into a lower atmospheric level where the clouds thinned or cleared. The dark was not literal emptiness, but a region of different optical depth, the light penetrating further before returning, giving back a darker tone. Voyager tracked it for months during its approach. Then the mission moved on, and when Hubble trained its instruments on Neptune years later, the spot was gone. It had dissolved back into the atmosphere, its material dispersed, its oval outline absorbed into the blue. In its place, in other years, other dark regions formed. Neptune generates them and releases them, the atmosphere always in motion, always rearranging. Uranus presents a different face. When Voyager 2 reached it in 1986, moving fast through the outer solar system on its long arc outward, the cameras returned images of a planet that seemed, at first, to have almost nothing to show. Pale, even, a smooth sphere of blue-green, without the banding or the storm ovals, or the dynamic cloud structures that had made Jupiter and Saturn so immediately vivid. Scientists looking at those images found the sameness difficult to explain. The planet had an atmosphere, it had weather in principle, it had circulation and temperature gradients, and enough energy arriving from the sun to drive some meteorological activity, and yet its face held still, offering almost nothing to distinguish one latitude from another. Voyager passed through the system in hours and continued into the dark beyond, carrying images of a world that seemed, on first observation, almost deliberately blank. The blankness was not the end of the story. Decades passed. The Hubble Space Telescope observed Uranus in the years that followed and continued to observe it as the planet moved along its orbit, an orbit carrying it slowly through a cycle unlike any other in the solar system, because Uranus tilts. Its rotational axis lies almost on its side, inclined at 98 degrees from the vertical, where every other major planet spins upright or close to it. Uranus rolls around the sun, its poles taking turns facing the solar wind directly. During the Voyager flyby, Uranus's south pole was pointed nearly straight at the sun. The planet's southern hemisphere had been in continuous daylight for decades. Its northern hemisphere had been in continuous night for the same span. The atmosphere, it turned out, had not been blank because it was inactive. It had been in a particular phase of a very long seasonal cycle, one whose timescale is measured not in months, but in decades. As the Hubble observations accumulated across the years following Voyager, the atmosphere of Uranus changed. Bands appeared, bright features emerged at mid-latitudes, sharply defined spots and streaks of cloud that moved and evolved over observation periods of days and weeks. The pole that had been in summer darkness began turning toward the sun as the planet's season shifted, and the atmosphere that had been locked in the stillness of one extreme began stirring towards something more active. What Voyager had seen was not characteristic of Uranus as a whole, but of Uranus in one specific and unusual moment of its 84-year trip around the Sun, a moment of atmospheric suppression at a particular orbital orientation, the planet's tilt, creating conditions that muted the visible circulation rather than driving it. The atmosphere of Uranus is cold, at the level called the tropopause, the altitude where temperature stops falling and flattens before beginning to rise again. Uranus registers approximately 53 Kelvin, which is colder than any surface temperature measured anywhere on Earth, and colder than the boiling point of nitrogen. Nothing in the familiar vocabulary of winter cold or Arctic stillness reaches that temperature. It is a cold that belongs to a different register altogether, the cold of a world that receives less than 0.25% of the sunlight that Earth receives at its surface, a world where the sun provides heat, mainly in the sense that it provides some. The tropopause sits at a pressure of roughly 1/10 of an atmosphere, a thin altitude well above the clouds that a distant observer would see, and it acts as a kind of thermal ceiling. Thermal ceilings matter because they regulate the movement of material above and below them. Warm air rises and cold air sinks. This is the fundamental engine of atmospheric motion everywhere in the solar system and on Earth and inside the sun itself. But when temperature stops falling with altitude and begins to rise, as it does above the tropopause, the usual logic reverses. The air above is warmer than the air below, and the vertical mixing that drives weather is suppressed. Material below the tropopause tends to stay below it. Material above tends to stay above it. The tropopause on Uranus is not simply a measurement. It is a boundary that separates the part of the atmosphere engaged in active circulation from the layers above, where a different set of processes governs what happens. Above the tropopause, in the stratosphere, both Uranus and Neptune display a temperature inversion. The air grows warmer rather than colder as altitude increases. The cause is absorption, methane, and its chemical relatives, including acetylene, take in ultraviolet and near-infrared sunlight and convert that energy into heat, warming the layers where they are concentrated. Acetylene forms when ultraviolet radiation breaks apart methane molecules, and the resulting fragments recombine in different configurations. It is a compound built by the atmosphere from itself, using the sun as a catalyst, and the heat it generates shapes the stratosphere in return. In the stratospheres of both planets, temperatures rise from the cold floor of the tropopause to several hundred Kelvin at higher altitudes, a temperature swing across a span of atmosphere that carries no pressure to speak of, that would feel almost tropical by comparison to the frozen layer below. Neptune's stratosphere holds one additional signal that scientists have watched change over recent decades. Following the Voyager flyby and continuing through ground-based and space-based telescope observations, Neptune's stratospheric temperature has been recorded shifting, cooling in some periods, and showing regional variations that do not match simple solar heating predictions. The planet is far enough from the sun that even small changes in the amount of sunlight reaching the stratosphere produce measurable temperature responses. Neptune's southern hemisphere had been in summer, in the slow seasonal sense, appropriate to a planet that takes 165 years to orbit the sun, during and after the Voyager encounter. As that long summer continued, the stratosphere warmed. As the planet's motion began carrying it into a new orbital phase, the pattern began to shift again. Each of these changes moves so slowly that observing them requires either a very long baseline of measurements or instruments sensitive enough to resolve the fine structure of a temperature field across a planet lying billions of kilometers away. Uranus's winds, measured at their strongest, reach roughly 900 kilometers per hour. That is fast by any standard the surface of Earth provides, but it is less than half of Neptune's peak wind speed, and the disparity has remained a persistent source of inquiry. Both planets receive very little sunlight, both are cold, both are comparable in size. The bulk of the energy that drives wind on a planet, at the very large scale, comes either from solar heating, differential warming of the surface, or atmosphere at different latitudes and longitudes, creating pressure gradients that drive flow, or from internal heat. Earth's atmosphere runs mostly on solar heating. Jupiter and Saturn are thought to be partly driven by heat escaping from their interiors. Neptune emits significantly more energy than it receives from the Sun, suggesting a substantial internal heat source. Uranus emits almost none. In this light, Neptune's more active and more violent atmosphere makes a certain physical sense. There is more energy available to drive it, arriving not from the Sun, but from within. The wind patterns of both planets organize themselves into broad east-west bands, parallel to the equator, like the bands of Jupiter and Saturn. Near the equator on Neptune, the winds blow westward, against the direction of the planet's rotation, a retrograde flow that is also seen on Uranus. At higher latitudes, the winds shift direction, becoming prograde, moving in the same sense as the planet's spin. This pattern of equatorial retrograde winds transitioning to high-latitude prograde winds is a feature of all four of the outer planets, a structural similarity that arises from how rotation shapes circulation in deep, thick atmospheres. The specific speeds, the specific latitudes of transition, the specific violence of Neptune's winds compared to Uranus's, these differ between the two worlds and remain areas of active study, their causes tangled up in questions about the internal heat sources and the deep structure of each atmosphere. In the upper reaches of both atmospheres, ultraviolet light from the Sun strips electrons from molecules, creating a thin ionized layer called an ionosphere. The molecules there are already sparse, the atmosphere so thin that pressure is a fraction of the pressure at Earth's surface, and the Sun's high-energy photons are energetic enough to crack molecular bonds and kick electrons free. The resulting ions drift in the weak solar wind that reaches this distance from the Sun, and they respond to the magnetic fields that both planets generate. Aurorae appear on both Uranus and Neptune, faint ribbons of light produced when charged particles from the solar wind are funneled into the atmosphere along magnetic field lines and collide with gas molecules there. They do not look like Earth's aurorae, and the geometry of the magnetic fields that guide them is much more complex than Earth's nearly aligned dipole, but the process is the same chain of events. A charged particle arrives, it follows the field, it strikes the air, and the air glows. The clouds of both planets are layered at different depths, corresponding to different temperatures and pressures. Methane clouds form at relatively high altitudes, in the pressure range around 1 to 2 bars, where temperatures are cold enough for methane to condense into ice crystals. Below them, at greater pressures and somewhat warmer temperatures, hydrogen sulfide clouds have been detected, particularly on Uranus, where spectroscopic measurements have provided evidence for hydrogen sulfide ice near the cloud tops. Ammonia clouds, which are prominent and visually dramatic on Jupiter, are less evident in the cloud decks of Uranus and Neptune, possibly because ammonia has reacted with other compounds at these depths, or possibly because the cloud layers are arranged differently in these colder atmospheres. Deeper still, at pressures of perhaps 30 to 40 bars, Water clouds are expected based on the temperatures calculated for those depths, but no instrument has yet sampled the atmosphere directly at those pressures to confirm them. The concept of cloud tops as a kind of visual surface deserves a moment of patient consideration. When Voyager photographed Uranus or Neptune, or when Hubble records their faces today, the images capture the layer where the atmosphere has become optically thick enough to reflect most incoming light back outward. Below that level, photons from the sun do not penetrate. The images show the top of a cloud deck, not a surface, below those clouds, in regions that no telescope has ever seen and where no probe has yet descended. The atmosphere continues for thousands of kilometers, growing progressively denser and warmer, the pressure increasing with every kilometer of depth. The cloud tops are a ceiling over an interior that has never been directly observed, a limit to what light can reach and return from. Everything known about the deeper structure of these planets has been inferred from the gravity they exert and the magnetic fields they produce, not from any direct sampling of their depths. Voyager 2 measured the temperature of Neptune's cloud tops during its 1989 flyby as approximately 73 Kelvin, colder than the boiling point of liquid nitrogen, colder than any solid surface in the inner solar system. The deep red light that methane has already absorbed does not reach those clouds, of course. The light that reflects from them is what is left after filtering, cool blue, the color of a sky seen from below through a very particular kind of air. That blue carries no warmth. It is the color of scarcity, the color of what the atmosphere has not yet taken. The cloud bands of Uranus in recent Hubble observations show a bright polar cap, a reflective region centered near the North Pole that has grown more prominent as that pole has moved into sunlight. It is thought to be a layer of methane ice haze concentrated in a broad descending circulation at the pole, a feature driven by the same extreme axial tilt that suppressed the atmosphere's visible activity during the Voyager era. As the northern pole receives increasingly direct sunlight during its long summer, photochemical reactions produce the haze material that settles into the cap. The bright cap is a seasonal phenomenon, one panel of a slow 4-panel cycle that will take the rest of a human lifetime and more to complete a single rotation. Bright storms have also appeared at Uranus's mid-latitudes in Hubble images and in ground-based observations made with large telescopes equipped with adaptive optics systems. These storms appear as white or pale features tracking steadily eastward against the band structure, some lasting hours, some lasting weeks before fading. Their brightness comes from methane ice clouds lofted to unusually high altitudes, catching the sunlight above the background haze. The processes that generate them, convective upwellings driven by localized heating or compositional instabilities within the atmosphere, are similar in kind to the convective storms on Jupiter and Saturn, but on Uranus they appear more rarely and with less spectacular violence, consistent with the planet's overall lower atmospheric energy budget. The tropopause cold minimum on Uranus, at 53 Kelvin, makes it the coldest tropopause temperature measured in the solar system. Neptune's tropopause, at roughly similar pressures, is warmer, around 57 to 59 Kelvin, depending on latitude and measurement period. Given that Neptune is almost twice as far from the Sun as Uranus, its comparatively warmer tropopause is a direct consequence of its internal heat source. The energy escaping from Neptune's interior warms the planet from below, producing a heat budget at the cloud tops that partially compensates for the planet's greater distance from the Sun. Uranus lacks this compensating warmth. Its tropopause holds the record for solar system cold because nothing from below is pushing warmth upward to moderate it, and the sun contribution at that distance and altitude is too slight to raise the temperature significantly. Between the tropopause and the cloud tops below, vertical mixing carries trace gases, haze particles, and photochemical products between levels. This region, the troposphere, is where the visible cloud activity occurs and where the temperature gradient drives convective overturning. On a planet with a strong internal heat source, this overturning can be vigorous and deep. On Uranus, where the internal heat is close to absent, the mixing is gentler. The atmosphere of Uranus behaves, in this sense, more like a slowly stirred fluid than a vigorously churning one. The circulation organized by rotation and by the energy that does arrive, rather than by any deep upwelling of internal warmth. Acetylene in the stratosphere, methane in the troposphere, hydrogen sulfide at the cloud tops, water ice somewhere deeper than any probe has reached. Each layer is a different chemical environment, each shaped by the temperature and pressure at that altitude, each contributing its own signal to the spectrum of light that arrives at any telescope aimed at these worlds. The atmosphere is a stack of thin layers, each governed by its own equilibrium, each exchanging material slowly with the layers above and below. No single layer tells the whole story. The spectrum of light returning from each planet is the sum of contributions from many depths at once, and separating those contributions requires both sensitive instruments and careful modeling of how light moves through a complex layered medium. In the summer of 1989, Voyager 2 passed through the system of Neptune in a matter of hours. After years of travel through the outer solar system, the spacecraft swept past the planet on a trajectory designed to bend it toward Neptune's large moon Triton, and in doing so passed close enough to the planet's disk to record temperatures, wind speeds, atmospheric composition, and magnetic field data in a single continuous observation arc. The data came down over the days and weeks following closest approach, decoded from radio signals sent across a distance of billions of kilometers. For the atmosphere of Neptune, that flyby produced the first and still the most comprehensive set of direct measurements ever made. For Uranus, a similar flyby 3 years earlier in 1986 had done the same. In both cases, science received a single pass, a single geometry, a single season, a narrow window through which to glimpse an atmosphere that had been turning for 4 billion years without any observer. Everything since has been built on extension and inference from those single moments of close observation, combined with the accumulating record of Earth-based and orbital telescope observations made in the decades following. The atmosphere of Neptune as Voyager saw it may not be the atmosphere of Neptune as it exists in any given year. The great dark spot that seemed so permanent in those 1989 images was gone when Hubble looked for it years later. Uranus, so still and bland in 1986, grew active and banded in subsequent years as its northern hemisphere emerged from its decades of winter. The atmosphere of a planet is not a single condition, but a continuous process, older than any human instrument and indifferent to any particular observation season. The visible face of both planets, then, is not a surface, it is a moving, layered threshold. Light arrives from the sun, already sorted by methane, into a palette of blues and greens. Clouds form at specific pressure levels, condense and sublimate, loft upward in convective columns, and thin again in descending regions. Wind moves the cloud material east and west, organizing it into bands. Storms appear within those bands and dissolve. Hazes settle from the stratosphere through the tropopause and into the cloud layer below. Photons that reach the cloud tops reflect back into space, and after 4 hours of travel, arrive at Earth. where a telescope might catch them and sort them by wavelength and extract from the pattern of absorption and reflection a set of numbers describing temperature and composition at various altitudes. This is how these atmospheres are known, not by touch or visit, not by descent into their depths, but by the careful interpretation of light that has passed through their outer layers and returned. The tropopause sits between that visible face and the deeper interior. Below it, temperatures begin to fall less steeply with depth and eventually reverse, rising as pressure increases. The chemical character of the atmosphere changes. The cloud layers have absorbed most of the sunlight that was going to penetrate. Below those clouds, the light does not go. The atmosphere there is lit only by the faint glow of its own warmth, conducted slowly through the fluid from whatever heat sources lie deeper, or released by the slow condensation of compounds, cycling through the cloud layers above. It is an interior sky, dark and warm and pressurized, where the familiar distinction between atmosphere and interior begins to dissolve. That dissolution happens slowly. There is no altitude at which the atmosphere ends and something else begins, no wall or surface or phase boundary that a probe descending through the cloud layers would suddenly register as a transition. The pressure increases smoothly, the temperature increases smoothly. The gas grows denser and denser, its molecules packed more tightly together, its behavior shifting from the diffuse and compressible character of ordinary atmosphere to something more like a thick, continuous fluid. The word atmosphere at those depths becomes imprecise. The word interior becomes more apt, though the transition between them cannot be placed at any single kilometer of depth. It is this gradual thickening, this slow surrender of one character and assumption of another, that marks the bottom of what can be observed from outside and the beginning of what can only be inferred. The tropopause marks the effective ceiling of the observable atmosphere, the thermal lid above which temperatures rise and below which they fall, the level where the atmosphere's organized visible behavior gives way to deeper processes that no photon returns from. It holds in place over both worlds, cold and still, by the standards of any other world in the solar system, unaffected by the slow accumulation of observations made from billions of kilometers away. It is where the outer face of these planets meets the interior, where the visible record ends and the inferred record begins, where the light turns back and the story continues in a different mode, in mathematics, in models, in the constraints imposed by gravity and density, in the shape of a magnetic field generated far below, in the dark, and the warmth and the pressure of a world that has been keeping its own counsel since before the earth had oceans. Below the last visible clouds, where the pale light from a distant sun has already faded into nothing, the atmosphere of Uranus thickens and closes overhead like water over a swimmer going down. There is no surface here to meet, no rock shelf, no ocean floor, no threshold you could press a hand against and know you had arrived somewhere solid. There is only the deepening, a gradual, continuous change in which the gas around you grows heavier and warmer and stranger, 1 kilometer at a time, the weight of everything above pressing down with a patience that has no limit and no interest in being measured. This is where the interior begins, if interior is even the right word for a place with no walls and no ceiling, only a direction, and that direction is down. Far above, in the cold upper atmosphere, hydrogen and helium drift as ordinary gas. They thin and spread the way gas does anywhere, filling whatever space contains them, moving in slow convective columns driven by the faint warmth that reaches this far from the sun. At those heights, they behave as expected. They follow the rules that gases follow everywhere. But the rules change with depth, and in an ice giant, they change faster than almost anywhere else in the solar system. The pressure at the visible cloud tops is close to what a diver might feel a few feet underwater on Earth. Familiar, barely noticeable, the kind of pressure the body adjusts to without complaint. A few 100 kilometers deeper, it is already something else. A few 1,000 kilometers deeper, it has become a number that resists ordinary comparison and asks instead to be felt as a quality of the place itself, a heaviness that saturates everything, that has no up and no relief, that is simply the texture of existing this far inside a world 14 times the mass of Earth. Uranus holds its atmosphere in a molecular hydrogen and helium shell that extends inward for several 1,000 kilometers from the visible cloud tops, and then keeps going into pressures measured not in bars, but in tens of thousands of bars. A single bar is roughly the weight of Earth's atmosphere, pressing down on every square centimeter of surface at sea level. Tens of thousands of bars is that weight multiplied until the comparison collapses under its own arithmetic. What matters here is not the number. What matters is what the number does to matter. At the base of the outer atmosphere, hydrogen still behaves more or less like the gas it is at the surface. Cold and expanding and responsive to temperature gradients, it moves in slow currents, rising where it is warmer, sinking where it cools, carrying heat upward from deeper layers toward the dark of space. But as depth increases, as pressure climbs steadily past any familiar reference, something in hydrogen's behavior begins to shift. The distinction between gas and liquid, which seems so clear at ordinary pressures, gas expands, liquid holds its shape, there is a surface between them, begins to soften, and then dissolve entirely. There is a state of matter called supercritical, and hydrogen enters it somewhere in the outer envelope of an ice giant, at conditions where temperature and pressure together push past the point where gas and liquid are meaningfully different from one another. It is not a phase transition in the way that water freezing is a phase transition. There is no sudden change, no boundary you could locate, no moment when everything shifts. It is instead a gradual convergence, the properties of the fluid moving smoothly from one regime into another without crossing any line. The substance just grows denser, it grows heavier. It fills its volume without gaps the way a liquid does, but it has none of the surface tension of a liquid, and none of the sharp boundary that a liquid holds against a gas. It is a single continuous phase, and the words that described it before, gas, liquid, have both become inadequate at the same time. This supercritical hydrogen is the medium through which the descent continues. Not invisible, not empty, it is dense and electrically neutral in the outer portions, carrying heat by convection as its temperature varies with depth, growing warmer and more compressed with every passing kilometer. The change is smooth. There is no surface to fall through, no boundary to mark on a map. There is only the deepening of the same continuous fluid, kilometer after kilometer, the pressure rising and the temperature rising with it, the matter becoming something that no instrument placed at the top has ever directly sampled, that no probe has ever descended far enough to reach. The outer planets in the solar system, Jupiter, Saturn, Uranus, Neptune, all have this supercritical hydrogen envelope in some form, but there is a structural difference in how it behaves at depth between the two planet classes, and that difference is one of the most important distinctions in planetary science. Inside Jupiter, the hydrogen envelope does not end at the icy interior the way it does in Uranus. It keeps going deeper and deeper into pressures that Uranus and Neptune never reach. At roughly 1 4/10 megabars of pressure, a megabar being 1,000,000 times the pressure of Earth's atmosphere at sea level. Something in hydrogen's behavior changes again, more dramatically. The electrons that normally stay bound to their protons can no longer hold their positions. The pressure outside them is simply too great. They are squeezed free. They begin to move through the surrounding material as freely as electrons move through a metal wire, and hydrogen, which began its life in Jupiter's interior as an ordinary gas, has become something that conducts electricity the way copper does. This is metallic hydrogen. It carries current. It responds to magnetic forces, and in Jupiter's vast interior, it occupies an enormous volume, a churning, electrically conductive fluid layer, thousands of kilometers thick, the likely engine of one of the most powerful magnetic fields in the solar system. Uranus and Neptune are smaller. Their interiors reach high pressures, certainly pressures that are extraordinary by any surface standard, but not the pressures that Jupiter's great bulk generates at comparable depths. The weight of the material above is simply less, and so the threshold at which hydrogen might transition into its metallic form, if it is reached at all in an ice giant interior, is reached only in a thin sliver, or not in a sustained, extended layer, the way it is in Jupiter. The metallic hydrogen phase that powers Jupiter's magnetic dynamo does not have a meaningful equivalent inside Uranus or Neptune. What these planets have instead, at the depths where metallic hydrogen would sit in a larger world, is the beginning of something entirely different: denser compounds, heavier materials, the icy mantle that gives these planets their name and their category. But that region lies deeper still, in the territory where the hydrogen envelope gives way. The hydrogen envelope itself, then, is a shell that surrounds the interior without fully defining it. It transitions from cold, sparse gas at the cloud tops to supercritical dense fluid at depth. It carries heat from below, distributes it in slow convective cells, and delivers it eventually to the atmosphere above. And then, over thousands of kilometers without a sharp edge, it fades. The proportion of hydrogen diminishes. The heavier compounds, water, ammonia, methane, and their mixtures, become more abundant. The character of the material shifts from the light, spreading quality of hydrogen to the denser, more complex chemistry of ices. Whether this transition happens at a single pressure horizon or gradually across a broad range of depths is one of the genuinely open questions in ice giant science. Interior models of Uranus and Neptune exist in several families, and they differ in exactly this detail. Some propose relatively sharp compositional boundaries between the hydrogen envelope and the icy mantle below, boundaries where the proportion of different molecules changes steeply over a small range of depth. Others propose a gradual blending, a gradient in which hydrogen slowly gives way to water and ammonia over thousands of kilometers, with no clearly defined layer where one ends and the other begins. The observations available to distinguish between these models are limited. Voyager 2 flew past both planets, Uranus in 1986, Neptune in 1989, and the gravitational measurements it made during those flybys remain, decades later, among the primary constraints on ice giant interior structure. Gravitational data of the kind Voyager collected tells scientists about how mass is distributed with depth, but it does not resolve fine structure. It admits a wide family of interior profiles that all fit the measured values. The question of whether the transitions inside these planets are sharp or gradual remains, for now, unanswered. What the models agree on is the general picture: hydrogen and helium, together constituting perhaps 15 to 20% of each planet's total mass, occupy this outer shell. They give the outer layers their gaseous, atmospheric character. They moderate the temperature gradient between the cold surface and the hot interior, and then they give way to the denser materials that make up the bulk of the planet, the water and ammonia and methane that justify the name ice giant and that hold the real mass of these worlds. Consider for a moment what the pressure gradient feels like in structural terms. In a gas giant as large as Jupiter, hydrogen dominates so thoroughly, for so long, through so many thousands of kilometers of depth, that the increase in pressure with depth is relatively gradual in proportion to the planet's total radius. There is room for a vast outer envelope of relatively lower density gas before the pressure climbs into the metallic hydrogen range. In an ice giant, the situation is different. The icy and rocky materials that dominate the deep interior are much denser than hydrogen. They contribute more mass per unit volume, and so the pressure gradient, the rate at which pressure increases per kilometer of depth, is steeper in proportion to the planet's size. The transition from the outer envelope to the denser interior happens over a smaller fraction of the total radius. The deep exotic conditions that in Jupiter sit far inside a thick padding of hydrogen are in Uranus and Neptune, closer to the surface in relative terms, their presence pressing upward through a thinner outer shell. This steeper gradient has consequences. It means that within a few thousand kilometers of the cloud tops, a distance that sounds vast, but represents only a fraction of Uranus's total radius of about 16,000 miles, ordinary compounds begin behaving in ways that bear no resemblance to their surface behavior. Water, under the temperatures and pressures of the deep hydrogen envelope and the region just below it, does not freeze, and it does not simply remain liquid. It enters states that have no analogy in any ordinary environment, states that only the most extreme laboratory conditions have ever briefly reproduced. The familiar molecule, two hydrogen atoms bonded to one oxygen, light and abundant and essential to life as it exists on the surface of Earth, has its geometry stressed and altered and ultimately dissolved by the conditions around it. It becomes something else, not by any change in its chemical composition, but by the pressure of its surroundings, forcing it into configurations that its ordinary form never holds. The hydrogen envelope, then, is not simply a layer that sits above the interesting regions. It is a conduit and a transformer. It takes the cold, spare material of the upper atmosphere and subjects it to a gradient of increasing density and temperature that prepares it for the transition into the deep interior below. It does this slowly, over thousands of kilometers, without drama, without a moment of visible change. It deepens, and the material in it deepens with it, until the word hydrogen becomes less useful than the words that describe what has replaced it. The pressure at the base of the outer hydrogen envelope, the rough transition zone where icy compounds begin to dominate, has been estimated in various models at tens of thousands of bars. Tens of thousands of bars is the pressure exerted by a column of water roughly 6 times the depth of the deepest trench in Earth's oceans, pressing down on every square centimeter of whatever lies beneath it. At those pressures, matter is not what it appears to be on any surface. The atoms within it have been pressed close enough together that their electron clouds begin to interact in ways that only occur under such compression. Chemical bonds that were stable at lower pressures come under strain. The geometry of molecules changes. The behavior of the bulk material diverges from anything measured in an ordinary laboratory, except in the most extreme and carefully controlled experiments. One of the enduring challenges of planetary science is that these conditions, which exist permanently and pervasively inside planets like Uranus and Neptune, can only be reproduced on Earth for nanoseconds, in volumes smaller than a grain of rice, by instruments that cost hundreds of millions of dollars and consume energy equivalent to a small city for a fraction of a second. The gap between the continuous, vast, steady interior of an ice giant and the brief, tiny, violent replications achieved in laboratories is immense. And yet those brief replications are the only empirical window available into what these materials actually do at these depths. The models that describe the hydrogen envelope, its extent, its transitions, its density profile, depend on equations of state, derived partly from theoretical physics and partly from these fleeting experiments, with the gravitational measurements from Voyager providing the external constraint against which everything is checked. The picture that emerges from this combination of theory and measurement and brief experiment is uncertain in its details, but clear in its outline. A hydrogen-dominated outer shell, gradually transitioning from cold gas to dense supercritical fluid, extending inward for several thousand kilometers, growing hotter and heavier with depth, carrying heat upward from the planet's interior by slow convection, and fading into the icy materials below by a gradient whose sharpness remains unknown. Within that shell, no metallic hydrogen layer of significance, no conductive hydrogen medium that could sustain a magnetic dynamo of Jupiter's type. Whatever generates the magnetic fields of Uranus and Neptune, and both planets have magnetic fields, strange and powerful ones, must come from something other than metallic hydrogen. It must come from the region below the hydrogen envelope, from the ionic and superionic materials of the deep interior, where water and ammonia under megabar pressures take on forms that have no ordinary name. The magnetic fields of these planets are not produced here in the hydrogen shell. They are felt here, threading upward through the envelope and out into the space above the cloud tops, where Voyager's instruments measured them decades ago. But their origin lies deeper, in the electrically conductive fluid that the icy compounds become under pressure. This matters because it draws a line between what the hydrogen envelope is and what it is not. It is a thermal shell, it is a pressure gradient, it is a slow conveyor of heat from inside to outside. But it is not, as it is in Jupiter, the seat of the magnetic dynamo. The hydrogen in Uranus and Neptune does not conduct electricity the way metallic hydrogen does in a larger world. It is electrically neutral in the outer portions, and even where it may approach the conditions of metallic hydrogen at the very base of the envelope, the extent and continuity of any such layer is too limited to generate a field as complex and powerful as what Voyager measured. The absence of a metallic hydrogen dynamo is, in its way, a defining characteristic of the ice giant class. Not what they have, but what they lack, a large enough interior to force hydrogen into permanent electrical conductivity over an extended volume. This absence is not a deficiency. It is simply the consequence of their size and composition. Uranus and Neptune are what they are, worlds just large enough to hold their deep interiors under extraordinary pressure, but not large enough to replicate the conditions that define a gas giant's deepest layers. Their magnetic fields arise differently from materials that are not hydrogen at all, and those materials begin where the hydrogen envelope ends. Somewhere in the region where the outer envelope thins and gives way, where hydrogen fades and the icy compounds gather and deepen, the character of the interior changes entirely. The smooth supercritical fluid of the hydrogen shell becomes something denser and more complex. The transition may be gradual, it may be sharp, the models differ, and the data cannot yet settle the question. What they agree on is that the change is real, that beyond a certain depth, the planet belongs to a different chemistry, and that the chemistry below is what makes these worlds ice giants rather than gas giants of a smaller type. The descent continues, the the material thickens. The pressure climbs past the range of any ordinary reference, and below the hydrogen shell, in the region where water and ammonia begin to dominate, the compounds that were volatile and cold in the outer solar nebula where these planets formed now exist in states of heat and compression that would be unrecognizable to the chemistry of any open air. They do not freeze there. They do not flow freely the way liquid water does. They exist in phases between these things, phases that have been given names only in the last few decades as laboratory techniques became capable of briefly reaching similar conditions. For now, the hydrogen envelope holds above, pressing the interior down with the weight of its own mass, carrying the sun's faint warmth outward in slow convective columns, its molecules drifting and cycling through a gradient that spans tens of thousands of bars from top to bottom. It is, in a way, the most ordinary part of this extraordinary interior. Hydrogen, the most abundant element in the universe, behaving as hydrogen does until the pressure beneath it makes that behavior impossible to sustain, and the planet becomes something that no familiar element alone describes. The outer shell of Uranus presses on every layer below it with a force that accumulates slowly, kilometer by kilometer, from the pale clouds visible through a telescope on Earth to the threshold where the hydrogen finally gives way. That threshold is not a line on any map. It is not a surface any instrument has crossed. It is, for now, a region in a model, a pressure range in an equation, a transition in a graph, and the graph sits in a laboratory where the researchers who built it have never stood closer to Uranus than any other person on Earth. The distance between the model and the reality is the distance between the third planet and the seventh, plus all of scientific uncertainty, which is its own kind of distance, and not a small one. There is something in the shape of this uncertainty that mirrors the shape of the interior itself. At the outer edge, in the atmosphere and the upper hydrogen envelope, the models are tightly constrained. Voyager measured the temperature and pressure profiles. Ground-based and space-based telescopes have tracked the cloud structure across decades. The equations of state for hydrogen and helium at these conditions have been tested in laboratories across many experiments. The picture is reasonably clear, but with depth, the constraints loosen. The gravitational data from a single flyby spreads across a wide family of acceptable models. The laboratory conditions that can probe the deep interior are extreme and fleeting. The material properties of water and ammonia at megabar pressures are known from a handful of experiments, not from the steady accumulation of data that ordinary chemistry enjoys. The deeper the model goes, the wider its uncertainty bounds, until at the center, the estimates of core mass span nearly a factor of 10, and the structure is more inference than measurement. This is the shape of the outer solar system as science currently holds it, clear at the edges, uncertain at the depths, rich with specific measurements that constrain without determining, and open, genuinely open, to revision as new instruments are built and new experiments find ways to push briefly into the conditions that these worlds sustain permanently. The hydrogen envelope, which seems like a beginning, the outermost interior layer, the first region below the visible sky, is in fact one of the better understood parts of the picture, precisely because it is composed of the simplest and most studied element in the universe. What lies below it is harder to know and stranger to describe, and the compounds that wait there under their extraordinary pressures are just beginning to be understood in the detail that might one day resolve the questions the models cannot yet answer. The supercritical hydrogen cools toward the cloud tops and warms toward the center. It carries the interior's warmth upward by convection, distributing heat into the atmosphere above. It maintains in this way a connection between the cold outer sky and the hot, deep interior, a slow thermal circulation that has been running without interruption for as long as the planets have existed. That circulation is one of the things scientists observe from outside to infer the inside. The temperature profile of the atmosphere, the heat flux at the cloud tops, the way the wind speeds at different altitudes imply circulation patterns that must connect to deeper dynamics. Each of these observations is a thread, and the model is the attempt to weave them into a picture of what no instrument has ever seen. And so the descent through the hydrogen shell is also, in a way, a descent through what is known toward what is inferred. The cloud tops are data, the tropopause is measured. The temperature and pressure profiles of the upper atmosphere have been traced with care across decades of observation. The transition into the supercritical hydrogen envelope is well understood in principle from the physics of hydrogen at high pressure, even if the precise depth and character of the transition inside Uranus specifically cannot be pinpointed. And then, deeper, the certainty thins the way the hydrogen itself does not. The models are still well reasoned. The physics that underlies them is sound, but the number of possible interiors consistent with all available measurements grows wider, not narrower, as the depth increases. In this, the interior of Uranus is not so different from many things that science studies: a certainty at the surface, a complexity below, an honest admission that the deepest structure is known only in outline and will be known in detail only when better instruments ask better questions from closer distances. There is nothing troubling in this. It is the ordinary condition of a science that takes seriously the distance between what can be measured and what can only be modeled. The hydrogen shell deepens and deepens and deepens, kilometer by slow kilometer, into pressures that accumulate like the weight of an ocean that never ends, until the composition of the interior changes and the hydrogen is no longer what carries the story. That change, that gradual or perhaps sudden shift from the lightest element to the compounds that define the ice giant class, is where the real character of these worlds begins. It is not far, in terms of the planet's radius, from the visible surface, but in terms of what the matter there does, what phases it inhabits, what properties it holds under the weight of everything above, it is as far from the ordinary chemistry of hydrogen gas as anything in the solar system manages to be. Below the base of the hydrogen envelope, the ice giant reveals itself. Not icy in any sense that the word ordinarily carries, not cold and crystalline and white, hot, under pressure, ionized, churning, a material that shares only its chemical composition with the water and ammonia and methane that drifted as cold grains through the outer solar nebula billions of years ago, and that now exist at conditions those grains could never have anticipated, and that no surface in the solar system has ever held. The hydrogen above it presses down, the rocky interior below it presses up, and between them, in the megabar range, the ices of the solar nebula have become something that only the most extreme physics adequately describes. The hydrogen shell, for all its depth, is the gentler layer. It is vast and pressurized and strange by ordinary standards. But by the standards of the deep interior waiting below, it is almost familiar, almost the kind of material that equations written in comfortable laboratories can fully describe, almost comprehensible to the chemistry of surfaces and open atmospheres. And then the pressure crosses a threshold, the composition shifts, and whatever ordinary comprehension has carried this far is left behind at the boundary between the outer envelope and the deep mantle, the way the last of the sunlight is left behind when the atmosphere closes over and the interior takes the place of the sky. The hydrogen was always, in this sense, a beginning, dense and strange to ordinary experience, but still composed of the lightest and most abundant element, still governed by physics that laboratories have tested across a wide range of conditions, still part of the outer shell of these worlds rather than their deep character. What the outer shell lacks, what no amount of hydrogen under even tens of thousands of bars can provide, is the electrical conductivity that would generate a magnetic field from within it. The metallic hydrogen that exists in Jupiter, vast and conductive and churning with electric currents, has no counterpart of significance in a world this small. And so the magnetic fields of Uranus and Neptune, real and measured and complex, must arise from something else, from the ionized ices below, from the electrically conductive fluid of water and ammonia under conditions far beyond the base of the hydrogen shell. The hydrogen envelope, then, presses down onto those materials with the accumulated weight of all the kilometers above it. It does this steadily, without change, without seasonal variation, without any of the dynamics that make the visible atmosphere so active. It simply rests in a state of continuous pressure upon the region where the real driver of these planets' magnetic fields exists. And through it, from below, the heat of that interior climbs slowly upward, conducted and convected through thousands of kilometers of dense pressurized fluid until it reaches the base of the observable atmosphere and disperses into the cold of the outer solar system. This is what the hydrogen envelope carries: heat from the interior, pressure from above, the slow pulse of a world that has been processing the energy of its formation for billions of years. The cloud tops register this process as weather. The atmosphere feels it as temperature gradients that drive wind. And the interior of hydrogen below the clouds holds it, maintains it, and delivers it, kilometer by kilometer, across the pressure gradient that separates the cold of space from the hot and electrically conductive materials waiting at the planet's deeper heart. Below the region where hydrogen still holds the shape of a familiar fluid, the pressure rises past the point where familiar things have names, temperature climbs, the weight of thousands of kilometers of material presses inward from every direction at once, and the substances that once drifted as cold grains in the outer dark of the early solar system, water, ammonia, methane, the simple compounds that built these worlds from the outside in, have become something that has no equivalent anywhere. A human instrument has rested, or a human hand has touched. This is the deep interior of Uranus and Neptune. It begins at a depth of several thousand kilometers below the cloud tops, where the pressure has climbed into the tens of thousands of bars and continues rising, and it extends inward through tens of thousands of kilometers more, through a vast region of ionized, electrically conducting fluid that the dominant current models describe as an ocean, not an ocean of water in any recognizable sense, but an ocean in the older, more structural meaning of the word. A deep, continuous, slowly moving expanse of matter through which currents circulate, carrying charge and heat, and the slow mechanical memory of the planet's rotation. The temperature here is estimated somewhere between 2,000 and 7,000 Kelvin, depending on depth and on which model is being used. At 2,000 Kelvin, iron on Earth would be vapor. At 7,000, the surface of the Sun is not much hotter. Inside Uranus and Neptune, that heat does not radiate away into space. It is held under pressure, compressed into a fluid so dense and so charged that it conducts electricity and generates through its slow motion the magnetic field that Voyager 2 measured from far out in space when it passed each planet in the 1980s. The ocean down here is not still. It turns very slowly in response to the planet's rotation and to the temperature gradients that exist between deeper and shallower layers. That turning motion, charged ions drifting in organized, large-scale patterns, is the best current candidate for explaining how these planets sustain their magnetic fields. No metallic hydrogen exists at the pressures and scales available inside worlds of this size. Something else must do the work, and the leading answer is the ionic ocean itself. Water and ammonia broken into fragments, their electrons stripped or redistributed, the remaining ions carrying charge as they move through hundreds of thousands of cubic kilometers of deep planetary interior. Water, under the pressures of this region, is not water. On Earth, water is familiar in its three ordinary forms. It freezes below a certain temperature and melts above it. It boils away into vapor and condenses back into rain. The transitions are clean and well known, and the molecule itself is stable across the full range of earthly conditions. But the phase diagram of water, the map of all the states it can occupy, organized by temperature and pressure, extends far beyond those three familiar forms into regions that were, for most of the history of science, purely theoretical. At pressures of hundreds of thousands of bars and temperatures of thousands of Kelvin, water enters phases that have no everyday names, because nothing in everyday experience creates the conditions needed to reach them. One of those phases is called superionic water. In superionic water, the oxygen atoms lock into a crystalline lattice. They do not move. They hold their positions against the immense pressure bearing down from above, forming a rigid grid that extends through the material the way atoms are arranged in ordinary ice, but under conditions that would vaporize ordinary ice in an instant. The hydrogen atoms, or rather, the bare hydrogen nuclei, the protons, stripped of their electrons by the surrounding heat and pressure, do not hold still. They flow through the oxygen lattice like a fluid. The material is at the same moment crystalline and flowing. It has the structural order of a solid in one element of its composition, and the mobile, current-carrying character of a liquid in another. The two behaviors coexist, not as a temporary or unstable compromise, but as a stable phase of matter that exists under those conditions, as naturally and as permanently as ice exists on a winter lake. For a long time, this phase existed only in equations and in computational models. Theorists had traced the lines on the phase diagram far into the high-pressure, high-temperature region and concluded that something like this must exist, that water under megabar pressures and thousands of Kelvin could not remain in any of its familiar forms. The models agreed with each other, but agreement between models is not the same as evidence, and the interior of Uranus and Neptune was not a place any instrument could reach. Then, in 2018, a group of researchers at Lawrence Livermore National Laboratory found a way to reach it anyway, briefly, in a laboratory, in a space smaller than a grain of rice, for a duration measured in nanoseconds. The experiment used laser-driven shock compression, powerful lasers fired simultaneously at a small water sample, generating a shock wave of extraordinary violence that propagated inward through the sample and compressed it, in the time it takes light to cross a room, to pressures exceeding 1 megabar and temperatures of several thousand Kelvin. Those conditions match what the models predict for depths of roughly 10,000 kilometers inside Uranus, not approximately, not as a rough order of magnitude, but with enough precision that the experiment could be meaningfully compared to the planetary interior. While the shock wave was passing through the sample, X-ray pulses generated by a separate laser source illuminated the compressed water and scattered off its atomic structure. The pattern of scattering, recorded by detectors placed around the sample, carries information about how the atoms are arranged. If the oxygen atoms had locked into a crystalline lattice while the hydrogen moved freely, the diffraction pattern would show it. It did. The structural signature of the superionic phase appeared in the data, matching the theoretical prediction, confirming for the first time that this form of water is real rather than merely calculated. The experiment lasted nanoseconds. The sample was destroyed. The conditions lasted for a duration so short that even the fastest mechanical process on a human scale would seem geological by comparison. And yet, in that nanosecond-long window, the experiment held the interior of Uranus. Superionic water exists. What exists inside these planets, in a region thousands of kilometers deep and thousands of kilometers wide, maintained at those temperatures and pressures not for nanoseconds, but for the full 4.5 billion years of the solar system's age, is a permanent ocean of superionic and ionic material that has been generating a magnetic field since before the Earth had a solid crust. The experiment's published results, described in Nature Physics by Millo and colleagues, did not resolve every question about the deep interior. They confirmed a phase, measured its structural signature, and anchored a point on the phase diagram that had previously been theoretical. The broader region of the interior, the full extent of the ionic ocean, the exact proportions of water and ammonia, and what remains of methane at different depths, the specific flow patterns that generate the magnetic field, all of this remains modeled, inferred, estimated from gravitational data and from laboratory approximations, rather than directly observed. But the confirmation that superionic water is real changed the nature of those models. It moved a central assumption from the category of theoretical necessity into the category of empirical fact, and the models built on that foundation now rest on something harder than the models that preceded them. Ammonia in the deep interior occupies its own extreme conditions. Under megabar pressures and high temperatures, ammonia, a molecule of one nitrogen and 3 hydrogen atoms in its ordinary form, breaks apart and reorganizes in ways that parallel what happens to water, though the details differ. The nitrogen atoms, heavier and less mobile than oxygen, form their own structural arrangements under pressure. The protons from the hydrogen atoms diffuse freely through the surrounding material, as they do in superionic water, carrying charge and contributing to the electrical conductivity of the ionic ocean. The precise phase behavior of ammonia under ice giant interior conditions is less completely mapped than that of water, partly because water has been the subject of more experimental attention, and partly because ammonia is harder to handle at the pressures involved. But the broad picture is consistent. Ammonia, like water, is not a molecule at these depths. It is a collection of ions, its atoms rearranged under pressure into configurations that bear no resemblance to the ammonia of a chemistry classroom, contributing its charged mobile components to the larger ionic fluid in which it is dissolved. Together, water and ammonia make up the great majority of the material in this region. They are the ocean. Their ions move through each other in patterns shaped by the planet's rotation, by the temperature gradients between layers, and by the slow, continuing release of heat from the planet's interior, and the magnetic field is the exterior signature of that interior motion, visible to instruments in space long before anyone understood what was generating it. Methane arrives at these depths in a different condition than water and ammonia. Methane, carbon bonded to 4 hydrogen atoms in its ordinary form, is a relatively fragile molecule under extreme pressure. The bond between carbon and hydrogen cannot hold against the megabar pressure range, and at depths of several thousand kilometers inside these planets, Methane is expected to have already decomposed. The hydrogen released from it rises into the surrounding fluid. The carbon, heavier and less mobile, sinks under the pressures and temperatures of the deep interior. Carbon does not simply dissolve, it is driven toward crystalline forms. Theoretical work and experimental evidence from facilities including the National Ignition Facility have traced the conditions under which carbon crystallizes in this environment. The pressures, the temperatures, the range over which the transition can occur. The crystalline form that carbon takes under these extreme conditions is not graphite. It is the form that carbon takes when pressure is high enough and the geometry of atomic packing is constrained accordingly. It is dense. It is hard. This is where the physics of the deep interior touches a striking possibility. Carbon crystallizing from a fluid, falling as slow precipitation through the ionic ocean, accumulating deeper in the planet over billions of years. That story belongs to its own exploration, and the chemistry of methane decomposition and carbon precipitation runs through a territory wide enough to warrant its own careful description. The point here is narrower. Methane does not survive intact at these depths, and its decomposition contributes hydrogen to the ionic fluid and carbon to the deeper layers, reshaping the composition of the interior over geological time. The ionic ocean, then, is not a static reservoir. It is a slow, churning, chemically active region in which the materials brought into these planets during their formation are continuously being sorted and transformed by the pressure and temperature gradient that runs from the outer boundary of the deep interior down to the rocky core below. Convection carries heat upward through the ionic ocean. Warmer material, slightly less dense, rises. Cooler material from above, cooler being a relative term in a region measured in thousands of Kelvin, descends to replace it. The cycle turns slowly, over time scales that dwarf human history, driven by the temperature difference between the hot inner boundary of the ocean and the relatively cooler material at its upper edge. That convection is central to understanding something that separates Uranus from Neptune in a way that the current models cannot fully explain. Neptune emits internal heat when all the energy Neptune receives from the sun is measured, and all the energy Neptune radiates back into space is measured. More comes out than goes in, roughly 2.5 times as much. Something inside Neptune is still cooling, still releasing the heat accumulated during the planet's violent formation, and that heat is escaping through the outer layers in a measurable, steady flux. Uranus does not. On Uranus, the measured internal heat flux is nearly zero, approximately 0.04 of a watt per square meter, a number so small that it is consistent with no internal heat source at all. By every standard model of how planets cool, Uranus should be emitting internal heat. It is roughly the same age, roughly the same mass, roughly the same composition as Neptune. The processes of gravitational contraction and radioactive decay that contribute to planetary heat should be operating inside Uranus at rates comparable to those inside Neptune. The numbers do not match what the instruments record. Something is trapping the heat. The most widely considered explanation involves a compositional gradient layer, somewhere within the Uranian interior, a region where density increases with depth, more steeply than temperature decreases, creating a barrier to the convection that would otherwise carry heat from the deep interior upward to the outer layers. In a planet where such a gradient layer exists, the hot deep interior cannot cool efficiently, because the fluid that would normally rise and carry heat away is prevented from rising by the density contrast between layers of different composition. The heat is locked inside, building up, or simply failing to escape, while the outer layers radiate only what the sun provides. What creates this gradient layer is not settled. One possibility is that the Ionic Ocean, rather than being well mixed throughout, has stratified layers of different composition, more water-rich regions alternating with more ammonia-rich or methane-rich regions that resist vertical mixing because of their density differences. Another possibility involves helium or heavier materials settling inward over time, creating a diffuse boundary that acts as a thermal lid. The models disagree, and the available observational data, gravitational moments measured by Voyager 2, the bulk mass and radius of the planet, the measured surface heat flux, cannot discriminate between the competing explanations with any certainty. What can be said with confidence is that Uranus, despite appearing from the outside to be a close twin of Neptune, is behaving very differently in its deep interior. Two worlds of similar size and similar composition, formed in similar regions of the solar nebula, have followed interior thermal histories that have diverged in a way that simple models did not predict, and that more sophisticated models can describe and outline, but not yet explain in full. The Ionic Ocean is also the source of what makes these planets magnetically unlike any other world in the solar system. Magnetic fields generated by convecting conducting fluids tend in most planets and stars to align roughly with the rotation axis. The field of Earth is inclined only about 11 degrees from the geographic poles. The fields of Jupiter and Saturn are more closely aligned still. Planets with convecting metallic interiors, rotating steadily, tend to generate organized, roughly dipolar fields centered near the axis of rotation. Uranus and Neptune do not. The magnetic field of Uranus is tilted approximately 60 degrees from its rotation axis. The field of Neptune is tilted roughly 47 degrees. Both fields are also significantly offset from the center of the planet. The point from which the field appears to emanate is not at the center of the sphere, but displaced toward one hemisphere. The resulting fields are complex, irregular, and poorly described by a simple dipole model. The most widely accepted explanation for this behavior points to the Ionic Ocean itself. If the conducting layer that generates the magnetic field is not at the center of the planet, but is instead confined to the outer part of the deep interior, a shell of conducting fluid, rather than a centrally located dynamo, then the geometry of the generated field will reflect the geometry of that shell, which does not necessarily align with the planetary rotation axis. Shallow dynamo models, in which the field generating region is a relatively thin layer near the outer boundary of the Ionic Ocean, rather than a deep central mechanism, can reproduce some of the observed features of these anomalous magnetic fields. This is another region where the Ionic Ocean connects the laboratory and the planet. The convective motion of electrically charged ions at pressures of hundreds of thousands to millions of bars, at temperatures of thousands of Kelvin, generating a magnetic field measurable by a spacecraft passing thousands of kilometers away. The chain from cause to effect runs across scales so different that each link in it requires its own set of experimental and observational evidence. And Voyager 2's data from those 1980s flybys remains, even now, the primary direct measurement of these magnetic environments. A single spacecraft passing each planet once, measuring the field as it flew by, is the full extent of the observational record from which these models are built. The science of the deep interior is in part the science of inferring an ocean from the ripple it leaves in space. The laboratory work that confirmed superionic water in 2018 belongs to a longer arc of experiments at facilities designed for high energy density physics rather than planetary beak science. Laboratories where lasers powerful enough to briefly replicate the interiors of planets are directed at samples measured in microns, and the signatures of matter under extreme conditions are recorded in the fractions of a second before the sample is gone. The National Ignition Facility, built in California for nuclear fusion research, has also provided a setting for experiments on water and other planetary materials at ice giant interior pressures. The equipment was not designed for planetary science. The instruments used to study fusion target behavior can, with modifications, capture the X-ray diffraction patterns that reveal the crystal structure of shocked materials. The experiments themselves are brief beyond comprehension, nanoseconds from laser pulse to detector reading, but the data they produce is physical and real, drawn from matter actually compressed to the pressures inside Uranus and Neptune, rather than extrapolated from lower pressure measurements or derived from theory alone. Each experiment adds a point to the phase diagram. Each confirmed point narrows the range of possible interior models. The map of what happens to water and ammonia and other planetary compounds under extreme conditions grows slowly with each run. The experiments do not last long enough to observe convection, or to watch ions move through a lattice, or to track any of the large-scale dynamic behavior of the real ionic ocean. They observe structure, the arrangement of atoms at a given pressure and temperature, and from that structure, the phase can be identified and the models can be calibrated. The dynamics of the ocean must still be inferred from gravitational data and from the magnetic field measurements and from the computational models that take the confirmed phase behavior as input. What the interior of Uranus or Neptune looks like, in the full sense of a visual picture, is not something science can currently describe. There is no light at 10,000 kilometers of depth inside one of these planets. Light at those pressures is not a medium that travels freely. It is absorbed, scattered, transformed by the dense material through which it would pass. The Ionic Ocean, if it could be experienced from within, would offer no visual information. Temperature and pressure would be the only immediate sensory facts. The crushing weight of material from above, the heat radiating from below, the slow drift of ions through a medium that is neither gas nor liquid in any familiar sense, but something denser and stranger that the ordinary vocabulary of matter cannot describe without stretching. What passes through the Ionic Ocean instead of light is the information encoded in the planet's gravitational field, the small deviations from a perfect sphere that result from the distribution of mass within the interior. Measuring those deviations precisely and over long periods is one of the primary ways a future mission to Uranus would improve the models. An orbiting spacecraft, tracking its own motion against the background of distant radio sources, can map the gravitational field in far greater detail than a single flyby permits. Each orbit, each small correction to the trajectory, carries a signal about where mass is concentrated inside the planet and where it is not. From that signal, the depth and thickness of the Ionic Ocean, the density contrast between the ocean and the layers above and below it, and the question of whether the interior of Uranus has a compositional gradient layer that traps its internal heat. All of these could, in principle, be constrained more tightly than current models allow. The Ionic Ocean would remain unreachable, but its outline, its weight, its thickness, the shape of the space it occupies inside these worlds would become less uncertain. The models built from Voyager's single passage would give way to models built from years of orbital measurement, and the picture of what hides inside these planets would gain resolution. There is a particular quality to the scientific knowledge of the ice giant interior. It is not the knowledge of observation. No instrument has entered this region. No measurement has been made from within it. It is the knowledge of inference and experiment, the gravitational signal of an interior whose mass distribution is constrained but not uniquely determined, the shock experiment that holds planetary conditions for a nanosecond and reads the atomic structure of the result, the theoretical models that extend known physics into pressure and temperature regimes far beyond their ordinary range of validation. This is knowledge of a very specific kind. It is confident in its broad features. The ionic ocean is real. Superionic water is real. The magnetic field is generated by convecting conducting fluid, and honestly uncertain in its details. The depth of the ionic ocean's lower boundary, the exact mix of water and ammonia, and their respective phase behaviors at each depth, the precise mechanism by which Uranus traps its internal heat, and Neptune does not. These are open, held as open, and will remain open until a mission provides the data needed to close them. The opening is not a failure of the science. It is the accurate picture of what is known and what is not, and it reflects the genuine difficulty of studying a place that is, by every current measure of engineering and physics, unreachable from the outside and entirely opaque from within. The Ionic Ocean turns, very slowly, inside these planets. It has been turning since before the solar system settled into its present arrangement. It will turn long after every human instrument, now in space, has gone silent. The water that flows through the oxygen lattice of the superionic zone, the hydrogen nuclei drifting through the rigid crystal, carrying charge as they go, has been in that state for billions of years, locked under pressure that will not relent, held at temperatures that will not fall for longer than the Earth has had continents. And at the National Ignition Facility, for nanoseconds at a time, that water exists again in the way it does at the depths of a distant world. The oxygen locked, the hydrogen moving, the diffraction pattern spreading outward through the detector, recording briefly what has been true inside Uranus and Neptune since before life on Earth had eyes to look at stars. The experiments end. The samples are gone. The data is real. Deep inside those two blue-tinted worlds, the Ionic Ocean continues. The ions drift and circle. The field lines trace their tilted, offset paths through the space around the planets, carrying outward the signature of everything that moves and charges and slowly turns in the dark and pressurized interior. The field was there before Voyager passed through it, reading its contours from hundreds of thousands of kilometers away, with instruments that registered its shape in a few hours of closest approach. The field will be there long after the record of that measurement has been interpreted and reinterpreted and built upon by models that grow steadily more careful and more constrained. What the laboratory confirmed in nanoseconds is what the planets have held for billions of years, a form of matter stable under conditions that only exist far from any place a human instrument has rested, real not because it was imagined or calculated, but because, briefly and definitively, it was measured. The superionic water of the deep interior is not a metaphor for strangeness. It is simply what water is at those temperatures and pressures, as naturally as ice is, what water is at the temperatures of a winter morning, as naturally as steam is what water is at the temperatures of a boiling kettle. Each form occupies its region of the phase diagram. Each is stable under its own conditions and unstable under others. The superionic phase happens to occupy a region that exists permanently inside 2 of the 8 planets in this solar system, and that same region has now briefly and actually existed inside a laboratory in California. The planets and the laboratory, separated by more than 1 billion miles, touched the same moment in the phase diagram of water, and the detector recorded it, and the data entered the literature, and the interior of these distant worlds became, in that small and precise way, slightly less hidden than it was before. The ions drift on, the field turns with the planet, irregular and offset, its tilt a record of the shell-shaped conducting layer that generates it, its asymmetry a signature of the Ionic Ocean's geometry, written large enough to be read from space. The pressure at the lower boundary of the ocean presses upward against the rocky core below and downward into it, and the rocky core presses back, and between them the planet holds its shape, cooling slowly, or in the case of Uranus, not cooling at all, its internal heat sealed behind whatever gradient layer holds it in, steady and vast and ancient. In the dark at the far edge of the solar system, two worlds whose interiors human instruments have barely begun to read. The slow current of the Ionic Ocean carries no awareness of the instruments that have tried to measure it from the outside, or of the experiments that have replicated it for nanoseconds in a laboratory, or of the models that have traced its likely properties through equations derived from physics, developed entirely within the thin, warm layer of a different, smaller planet, far closer to the Sun. The Ionic Ocean simply is dense, charged, ancient, warm, turning in the deep interior of worlds that formed from the cold grains of the early solar nebula, and have been holding their heat and generating their fields and slowly sorting their chemical constituents ever since. And in laboratories where lasers still fire at water samples smaller than a grain of sand, the map of what is possible under those conditions grows, one confirmed data point at a time, patient and methodical, toward a fuller picture of what hides inside those two distant, similar, and still strange worlds. At the center of Uranus, the pressure reaches somewhere between 6 and 8 megabars. A megabar is 1,000,000 times the weight of the atmosphere pressing down on the surface of the Earth. 6 of them stacked, 8 of them perhaps. The number does not compress into something the body can hold. It arrives instead as a quality, a texture, a sense that at that depth, the word rock no longer names anything recognizable, that the silicate minerals forming the core of that world have been pressed into configurations that no geology on any surface anywhere has ever produced. The temperature at that center is estimated somewhere between 5,000 and 7,000 Kelvin. That is hotter than the visible surface of the sun, held inside a planet that from the outside appears cold and distant and blue-gray in the dark. The heat is old. It was gathered during the formation of the planet, locked in as the material fell inward and compressed, and it has been working its way outward through thousands of kilometers of dense ionic fluid and slowly churning icy mantle for 4.5 billion years. Some of it reaches the surface, some of it does not, and the question of which planet releases its heat and which one holds it sealed inside is one of the stranger open puzzles in the study of the outer solar system. The core itself is small, proportionally. Interior models built from the only data available, which is the way each planet's gravity tugs at a spacecraft passing close place. The rocky center at somewhere between half an Earth mass and 4 Earth masses. Its radius is perhaps 15 to 25% of the planet's total radius. That is a wide range. The uncertainty is not a failure of the science, but an honest reflection of what a single flyby, decades ago, was able to determine. The gravitational field of a planet bends the path of a spacecraft in ways that depend on how mass is distributed inside, and the measurements from those flybys were precise enough to rule out many possibilities, but not precise enough to settle on one. What the gravitational data describes is called the planet's gravitational moments. The two most important carry the designations J2 and J4. They measure how much the planet's gravity deviates from a perfect sphere, how much mass is concentrated at the equator versus the poles, how the internal density varies with depth. Voyager 2 measured these values for both Uranus and Neptune during its flybys in 1986 and 1989, respectively. Those measurements remain, to this day, the most precise direct observational constraints on the internal structures of both planets. No other spacecraft has visited either world since. From those two numbers, J2 and J4, planetary scientists have constructed families of models, each one a slightly different picture of what the interior might look like in detail. The models agree on the broad outlines: a hydrogen-rich outer shell, giving way to a deep interior dominated by water, ammonia, and other dense compounds, with a rocky region at the center. But they disagree on the sharpness of the boundaries between layers, on the precise distribution of mass with depth, on whether the transition from one material to the next happens quickly or slowly over thousands of kilometers of gradually shifting composition. A wide family of different interior profiles can all produce J2 and J4 values that match what Voyager measured. The data does not choose between them. The core mantle boundary, if one exists in a clean sense, is likely nothing like the boundaries drawn in cross-section diagrams. High-pressure experiments on mixtures of silicate rock and water, and silicate rock and ammonia, suggest that at the temperatures and pressures near the center of an ice giant, the rock does not simply sit there as a solid foundation. Silicate minerals, under those conditions, may partially dissolve into the surrounding fluid. The boundary between the rocky core and the icy mantle above it may be less a surface than a gradual dissolution, the rocky material softening, dispersing, merging by degrees with the dense fluid pressing in from above, so that the edge of the core is somewhere in a broad zone of transition rather than at a defined line, a shoreline at high tide, where the water moves into the sand and the sand becomes the water, and there is no single place that is entirely one or the other. The temperature at that depth drives silicate components into solution. The pressure keeps them there. The result is not a clean two-layer system, but something more blended, more continuous, the rock and the fluid occupying the same region in a state that is neither fully one nor the other. This is what laboratory experiments at the extremes of achievable pressure suggest. The experiments themselves last fractions of a second, driving shock waves through tiny samples and reading the structural response through X-ray diffraction before the sample returns to ordinary conditions. The picture they build is assembled from glimpses, not from sustained observation, and yet those glimpses, repeated and refined, have produced a genuinely different understanding of what planetary cores are like than the one the diagrams implied. There is, sitting at the edge of all this, an anomaly that no standard model of planetary cooling has explained. Uranus and Neptune formed at roughly the same distance from the Sun. They accreted from similar material. They have similar masses, similar compositions, similar structures, as best as can be determined. By every expectation, they should be losing their internal heat at roughly comparable rates, their interiors cooling on similar timescales, their surfaces radiating similar amounts of warmth into space. Neptune does this. Neptune emits roughly 2.5 times the energy it receives from the Sun. That excess comes from inside, from the slow release of heat left over from the planet's formation, conducted outward through the interior and radiated from the upper atmosphere. The value is approximately 4 watts per square meter at Neptune's surface, a small number in absolute terms, but significant against the faint sunlight arriving at that distance from the Sun. Uranus radiates essentially nothing. Its measured internal heat flux is approximately 0. 0.042 watts per square meter. The planet appears in thermal terms to be in balance with the sunlight it receives, no internal warmth rising to supplement it, no excess to detect. For a planet of its mass and composition and age, this is very close to impossible under standard models of planetary cooling. Something inside Uranus is holding its heat. Something is preventing the slow outward movement of warmth that has, over 4 billion years, allowed Neptune's interior to continue cooling and ventilating its ancient energy. The leading candidate is a compositional gradient, a region inside Uranus where denser material sits beneath lighter material in a stable configuration, preventing the convection that would otherwise carry heat upward. If a layer exists where the fluid composition changes with depth in just the right way, the buoyancy forces that drive convection could be suppressed. The heat would accumulate at depth rather than rising, held down by the weight of denser fluid above, unable to find a path to the surface. The planet would cool from the outside in and never fully ventilate its interior. This is a hypothesis, not a settled picture. It is the best current candidate for explaining the divergence between two worlds that should, in almost every way, look the same. The gradient would have to be maintained against mixing over billions of years, which raises further questions about how such a stable layering could persist. There are competing ideas. None of them is confirmed. What is confirmed is the measurement. Uranus is cold at its surface in a way that Neptune is not, and the difference, expressed in watts per square meter, is a number that sits quietly at the center of the field and has not yet been fully resolved. The two planets hang in thermal infrared side by side in the imagination. Neptune brightens slightly, not in visible light, not in the blue of its methane-colored atmosphere, but in the longer wavelengths that carry heat rather than color, a faint, even glow distributed across its disk, the warmth of 4.5 billion years still working its way out. Uranus beside it does not glow. It is even. It accepts the sunlight it receives and returns it, and nothing more comes up from the depths. Two similar worlds, and between them, in the thermal infrared, a gap that one number can measure and no model has yet fully closed. The magnetic field of each planet adds another layer of strangeness. Both Uranus and Neptune have magnetic fields unlike those of any other planet in the solar system. Earth's magnetic field is roughly aligned with its rotation axis, tilted by about 11 degrees, close enough to the geographic poles that compasses are useful. Jupiter's field is tilted by about 10 degrees. Saturn's is nearly perfectly aligned. But Uranus's magnetic pole is tilted by approximately 60 degrees from its rotation axis, and Neptune's by about 47 degrees. More than this, the magnetic fields of both ice giants are offset from the planet's center, Uranus's by roughly 1/3 of the planet's radius, Neptune's by a similar proportion. The field does not emanate from the center of the planet as a simple dipole. It is generated somewhere off-axis in a shell or region within the interior, and the resulting magnetic field is complex and asymmetric in a way that makes the fields of the other giant planets look orderly. The most widely accepted explanation for this is that the magnetic fields of Uranus and Neptune are not generated deep in the center, the way Earth's is thought to originate in its iron outer core, or the way Jupiter's may arise in its vast layer of conducting metallic hydrogen. Instead, the ice giant's fields are thought to originate in the Ionic Ocean, the deep conductive fluid of water and ammonia ions that fills much of their interiors. The convection of this fluid, driven by heat and rotation, generates electric currents, and those currents produce magnetic fields. Because the Ionic Ocean does not occupy the center of the planet, but rather a shell at some depth. And because the shell may convect in complex, non-uniform patterns, the resulting field is tilted and offset in the way that Voyager's magnetometer recorded. This is a picture with real explanatory power. It connects the strange geometry of the magnetic fields to the physical properties of the ionic interior in a way that is mechanically plausible. And yet the details, which parts of the ionic layer are most conductive, how the convection patterns form and change over time, how the depth and composition of the layer affect the field geometry, these remain incompletely understood. The magnetic measurements from Voyager are precise records of what the field looked like on 2 specific days, decades ago. Whether it has changed since then, whether it fluctuates on long time scales, whether the offset and tilt are stable features or vary over planetary history, none of this is known. Voyager 2 is now far beyond the orbit of Neptune, moving through the interstellar medium at roughly 55,000 kilometers per hour, carrying instruments that still transmit faint signals back to Earth. It is the only spacecraft to have visited Uranus and Neptune. Its encounters with those planets lasted hours. The data it returned, the gravitational moments, the magnetic field measurements, the atmospheric temperatures, the wind speeds have been the primary empirical basis for ice giant science for nearly 4 decades. The models built on that data are sophisticated and carefully reasoned, and they remain constrained by what a single flyby could sample. In the wider solar system context, the rarity of that data becomes more apparent. Mars has been orbited by spacecraft continuously since 1997. Jupiter has been orbited for years at a time by multiple dedicated missions. Saturn received 13 years of close study from the Cassini spacecraft, which measured its gravitational field in such detail that modelers could constrain the structure of Saturn's interior with a precision that remains unavailable for either ice giant. The Galileo probe dropped into Jupiter's atmosphere and transmitted composition and pressure data from below the cloud tops until the pressure crushed it. Nothing like this has been done for Uranus or Neptune. The scientific case for sending an orbiting spacecraft to Uranus has been building for decades. The planetary science community, through the process by which it sets collective research priorities across a 10-year period, has now placed a Uranus mission at the top of its list. The recommendation, formalized in the most recent decadal survey, calls for a flagship spacecraft capable of entering orbit around Uranus and deploying a probe into its atmosphere, a probe that would descend through the cloud layers, transmitting measurements of temperature, pressure, and chemical composition from altitudes that no instrument has ever reached before the pressure eventually ends its transmission. The orbital phase of the mission would last years. The spacecraft would make slow elliptical passes around the planet, its radio signal tracked from Earth with enough precision to map the gravitational field in detail many times finer than what Voyager's flyby allowed. Each pass would add another set of measurements. Each set would tighten the constraints on interior models, the wide family of acceptable density profiles that the current data permits would narrow, pass by pass, towards something more specific, not certainty, but a smaller range of uncertainty, a picture with fewer competing versions. The gravitational mapping alone would transform the field. J2 and J4 constrain the interior, but leave much open. An extended orbital mission would measure higher-order gravitational moments, J6, J8, and beyond, that encode finer detail about the distribution of mass inside the planet. These numbers would allow modelers to discriminate between interior structures that the current data cannot separate. The question of whether the transitions between layers are sharp or gradual, one of the fundamental unresolved structural questions might begin to yield. The question of whether the core is a discrete rocky body or a diffuse dissolution zone might come closer to an answer. The atmospheric probe would carry its own set of revelations. The composition of the deep atmosphere, the precise ratios of water, ammonia, and methane below the cloud tops, where condensation masks them from remote sensing, would allow direct comparison with what the models assume about bulk interior composition. If the measured abundances match the model assumptions, the models are better supported. If they diverge, the models must change. Either outcome would be progress, the kind that can only come from an instrument physically inside the environment it is measuring, rather than reading it from thousands of kilometers away. The mission has not yet been built. The spacecraft does not yet exist. The probe has not been designed. What exists is the recommendation and the reasoning behind it, and the weight of 30 years of science conducted on data gathered in a matter of hours. The mission, if it proceeds on schedule, could reach Uranus sometime in the 2040s, a decade and a half of travel across a solar system whose outer edges take the light of the sun 4 hours to reach. In the years between now and then, the science continues with the tools available. Ground-based and space-based telescopes image the cloud tops and track atmospheric changes through Uranus's long seasonal cycle. Laboratory experiments drive shock waves through water and ammonia samples and refine the phase diagrams of materials under extreme pressure. Theorists build and test interior models, adjusting the assumed layer structures and compositions until the calculated gravitational moments and magnetic field geometries best fit the available measurements. The picture deepens, slowly, from the outside. There is something particular about studying a planet by inference, by the slight bend of a radio signal, by the deviation of a gravitational field from a perfect sphere, by the tilt of a magnetic pole, by the presence or absence of thermal emission. It is a kind of reading without direct access, a reconstruction from evidence rather than from observation. The rock at the center of Uranus has never been seen. The ionic fluid thousands of kilometers inside Neptune has never been sampled. The superionic water that experiments briefly achieve in a laboratory in nanoseconds under pressures built with lasers gives a glimpse of what may exist permanently and quietly inside those planets. But the glimpse is indirect, inferred, held together by the consistency of multiple lines of evidence rather than by any single definitive measurement. This is not a weakness of the science. It is the condition of the science. Most of what can be known about the interiors of planets must be inferred rather than observed, because no instrument can reach the depths where the most interesting conditions exist. The inferences are careful and constrained and honest about their own uncertainty. They rest on the same physical laws that govern the laboratory and the surface of the Earth, applied at scales and pressures and temperatures that make the application challenging but not impossible. The models may be revised when better data arrives. The revisions will be progress. The outer solar system is, at the scale of the solar system, close. Neptune is approximately 30 times the distance from the Sun to the Earth. That is a number that compresses poorly into felt experience. Light from the Sun takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune. The signal from Voyager 2 in the interstellar medium takes more than 20 hours to arrive. The scale is vast, the distance is real, and a spacecraft sent now would spend 15 years or more crossing it before the science could begin. But the distance is not infinite. The physics is understood. The trajectory is calculable. The mission is not a dream deferred indefinitely, but a concrete proposal and an active planning process, with an estimated cost and a candidate launch window and a community of scientists who have spent careers preparing for what it might find. In the deep interior of Uranus, in the region where the ionic fluid meets the beginnings of the rocky center, the pressure is such that silicate minerals have likely dissolved into the surrounding fluid to some degree. The boundary is not a floor, it is a transition, a gradual shift from one material character to another across a zone that may span hundreds of kilometers. The heat flowing outward from the deep center, if it flows at all, must pass through that transition zone, through the ionic ocean, through the outer shell of dense fluid hydrogen, and finally into the atmospheric layers that eventually radiate what reaches them into space. Most of it does not reach the surface. Most of it, by the evidence of the thermal measurements, is held inside, contained by whatever compositional gradient maintains the stability that prevents convection. The heat that formed when the planet was young, the energy of infalling rock and ice, the compression of accreting material, the gravitational potential converted into warmth over millions of years as the planet assembled, that heat is still inside, 4.5 billion years old, stored in the deep interior of a world that has been rotating in the dark outer solar system since before the Earth had its continents. It does not escape, it waits. Whether waiting is the right word for a physical process, with no capacity for experience, is a question the language encourages, and the physics does not. Neptune, by contrast, continues to lose its heat. The ionic fluid inside it convects. The warmth works its way outward through the layers. At the cloud tops, it radiates away into space as infrared light, faint and measurable, detected by spacecraft and ground-based telescopes sensitive to those wavelengths. Neptune is cooling. It will continue to cool for a very long time. The process that began when the planet formed, the slow release of the energy of formation, is still ongoing and will be ongoing long after any instrument built by the civilization currently studying it has ceased to function. The two planets will continue in their orbits. Uranus completes one orbit of the Sun in approximately 84 years. Neptune takes about 165 years. At those distances, the Sun is a bright star, intensely luminous against the dark, but not the overwhelming presence it is from the inner solar system. The light it provides is enough to drive the atmospheric chemistry that colors the planets, enough to drive seasonal variations across Uranus's long and peculiar year, but not enough to warm the surfaces or heat the interiors in any meaningful way. The planets are cold at their outer boundary and hot at their center, and between those extremes lies the interior, the ionic fluid, the dense compounds, the slowly churning material that generates the magnetic fields that were measured once, briefly, decades ago, and have not been measured since. The Voyager 2 spacecraft crossed the magnetic envelope of Neptune on the 25th of August, 1989. Its magnetometer recorded the structure of the field as the spacecraft moved through it. The tilt, the offset, the complexity of a magnetic geometry, unlike anything the mission had encountered at Jupiter or Saturn. The data streamed back across the hours of distance to Earth, where researchers converted the radio signals into numbers and the numbers into a picture of a magnetic field generated deep inside a world that no probe had ever entered. That picture is still the only direct measurement of Neptune's magnetic environment that exists. Something about the persistence of that single measurement, its continued status after decades, as the last word on the subject, carries a particular weight. Science moves quickly in some areas. New telescopes, New computational methods, new theoretical frameworks, the accumulation of data from ongoing missions. In many areas of planetary research, the picture changes year by year. But at Uranus and Neptune, the fundamental direct measurements have not changed since the 1980s because no new direct measurements have been made. The science has grown enormously in its models and its laboratory work and its theoretical sophistication. The observational base, the direct data from inside the magnetic environments and above the cloud tops and through the gravitational fields of those planets, has remained fixed at what a single spacecraft gathered in two brief encounters at the end of the last century. The proposed orbiter would change this. It would arrive at Uranus, assuming the mission proceeds, and begin making measurements that Voyager never could. The gravitational field, mapped continuously over years rather than sampled once in hours. The magnetic field measured at multiple latitudes and at multiple points in its rotation, building a three-dimensional map rather than a single traverse. The atmosphere sampled in situ by a descending probe rather than read by instruments thousands of kilometers above it. The data would be dense and varied and would arrive not in a single burst, but in a slow accumulation across the years of the orbital phase, each transmission adding to a picture that grows more detailed and more constrained as the mission continues. The scientists who would conduct that mission are working now. They are building instruments, testing designs, writing proposals, making the case for this particular planetary destination in competition with many other worthy scientific priorities. Some of them have spent their entire careers working with the Voyager data, refining models built from those brief flybys, pushing the science as far as it can go with what was collected. Some of them are recent graduates who have never known a time when the Voyager flybys were recent events. The mission they are working toward would, if it proceeds, produce data in the 2040s and 2050s that would redefine what is known about ice giant interiors in ways that are not yet predictable, because the specific nature of what will be found cannot be anticipated from the outside. There is a long patience in this. The timescales of planetary science are not the timescales of a single career or a single life. The Voyager missions were conceived and built and launched in the 1970s. The data from those missions is still in active use. The planetary scientists who designed the instruments that measured the gravitational fields of Uranus and Neptune are mostly no longer working. The scientists who will analyze the first orbital gravitational field data from a Uranus orbiter have not yet completed their educations. The science passes through generations of researchers, each one building on what came before, each one working at the edge of what the available data can support, and the instruments they eventually send will carry forward the work of everyone who shaped the questions those instruments will answer. At the center of Uranus and the center of Neptune, the conditions that no instrument has directly measured continue as they have for 4 billion years, unchanged by the state of knowledge about them. The pressure presses, the temperature holds. The rock at the center, if rock is still the right word for what exists under those conditions, maintains whatever configuration pressure and heat have imposed on it. The ionic fluid above it churns or holds still, convects or stratifies according to the physics of the materials and the thermal structure of the interior. The magnetic field, generated somewhere within that fluid, maintains its tilted geometry and its offset from the center and extends outward through the planet and into the surrounding space where Voyager measured it once, and where a future orbiter would measure it many times over many years. The planets hold their interiors quietly. Whatever is inside them has always been inside them, from the first compression of material in the outer solar nebula to this moment, the heat of formation, the iron and silicate of the rocky core, the water and ammonia in their exotic phases, the methane broken down by pressure into carbon and hydrogen, the carbon settling slowly. All of it has been there through the 4.5 billion years during which the sun has been burning, through the long cooling of the inner solar system, through the formation and extinction of species on Earth, through everything that has happened in the warmth of the inner planets, quietly inside, undisturbed. The outer solar system at night, from the vantage of any of the inner planets, appears as a band of faint stars. The planets at those distances are not visible to the naked eye unless conditions are right, and even then they are points of light without feature, indistinguishable from the stars around them except by their slow movement against the background. The enormity of what is inside them, the heat, the pressure, the exotic states of matter, the churning fluid that generates the magnetic field, the rocky dissolution at the core, none of it is apparent from outside. They look like light. They are much more than that, and the science of what is more than that is still, in many of its most important aspects, a set of careful inferences built on very little direct data and held open for the measurements that have not yet been made. The spacecraft that will eventually orbit Uranus will do so in silence, in the dark, far from the warmth of the inner solar system, its instruments pointed inward at the planet, its radio transmitter pointed back toward a small blue point of light that is the Earth. The transmissions will take hours to arrive. The researchers who receive them will spend months and years analyzing what they contain. The models they build from that analysis will be more constrained than the ones that exist now, less uncertain, built on the accumulation of gravity measurements and magnetic field maps and atmospheric composition profiles that Voyager's brief flybys could not provide. The picture will not be complete. It will never be complete, in the sense that some final comprehensive knowledge of the interior of another planet is not a thing that science achieves in a single step or a single mission.